Assalamu alaikum. My name is Hafiz Waleed Zahid, roll number 21 TE83 from Telecommunication Engineering Department UED TAXILA. So we performed lab task 3 of digital signal processing. This is the first task. We defined function that name this that takes 3 input argument and not n1 and n2 and returns 2 output arguments x and n. The second line creates a vector n that represents the range of value from n1 to n2. And the last line creates a vector x that represents the unit impulse function delta n minus n naught. It uses logical indexing to set the value to 1 where the condition n minus n naught is equal to 0 is true and 0 otherwise. This condition is true only when n is equal to n naught, resulting in a unit impulse at that point. So in this code, we call the function with argument 0 to minus 5 and 5. It assigns the output values to variable x, n and n. The resulting xn is the unit impulse sequence and n is the corresponding range of values. This line creates subplot with a 1 row and 2 column and selects the first subplot indicated by 121, and it uses the plot function to plot the unit impulse sequence xn against the values of n. The subplot shows the continuous line plot. In this code generates 2 subplots side by side. The first subplot displays a continuous line plot of the unit impulse sequence and the second subplot displays a stem plot of the same sequence, providing different visualization of data. So in task 2, it generates a subplot with 2 plots side by side. The first plot is a continuous representation of the unit step sequence using plot, and the second plot is a discrete representation using stem function. The axis command are used to set appropriate limit for better visualization. The unit step function is defined over the range minus 5 to 5, and the plot shows the step occurring at n is equal to 0. So in task 3, it constructs a unit step sequence by iteratively adding shifted impulse sequence. The loop runs for 11 iterations, each time incorporating a new term in the sum. Within each iteration, a 1-second pause is introduced to visually observe the evolving unit step sequence. The stem plot illustrates the current state of the sequence, updating the title and labels accordingly. And the hold on command ensures that each plot is superimposed, allowing the visualization of the cumulative effect of adding impulse sequence. And the hold off command releases the hold, completing the process and providing a step-by-step representation of the unit step sequence as the sum of shifted impulse sequences. So in task 4, we construct 3 arbitrary signals x1, x2 and x3 using a sum of scaled and shifted unit impulse sequences. Each signal is visualized in the first subplot, while the construction process is demonstrated in subsequent subplots. The loop iterates through each element of the signals, obtaining the corresponding unit impulse sequence through the assumed function. The cumulative sum of the scaled unit impulse sequences from the reconstructed signal, and the script employs the pause command for a brief delay, allowing for the visual observation of the construction process. The hold on and hold off commands are used to superimpose plot and maintain the display of each step in the sequence construction. So in task 5, the even odd function decomposes a real sequence x into its even xe and odd x0 components. It begins by validating the input sequence is real, raising an error if it contains a non-zero imaginary part. The function then constructs mirrored time indices and determines the common range between the original and mirror indices. After aligning the signal with the mirrored indices, it pads the signal appropriately to ensure both sequences are defined over the same range. The even and odd components are calculated using specific formulas. The result is decomposition of the input signal into even and odd parts. Returned along with the mirror time indices, the function is designed to handle real sequences and provides a useful tool for signal analysis being based on symmetry properties. So in last task, this MATLAB code generates and plots a continuous time signal, specifically a cosine wave. The signal is defined over the time interval t ranging from 0 to 2 seconds with a sampling interval of 0.005 seconds. The frequency of the cosine wave is set to 1 Hz, and the cos function is used to create the cosine signal. And the resulting signal is plotted using the plot function. The subplot command divides the figure window into 2 subplots, and the cosine signal is displayed in the first subplot. The title Y label and X label function are used to provide a title to the plot and label the axis with information about the signal. The resulting plot visually represents the continuous time cosine signal with a frequency of 1 Hz over the specified time interval.